Hello everyone and welcome. In this video we're going to talk about the structure of the 20 different amino acids, and we'll talk about how can the structure really correlate to the properties of the amino acids, and then we'll also talk about determining the isoelectric point and drawing the titration curve. So let's start with the basic structure of an amino acid, which contains a carboxylic acid group, right? We'll draw it protonated for now. And it has an alpha carbon, and that alpha carbon is connected to an amino group. All right, so if we take a minute, so that's the basic structure, a carboxylic acid group, an amino group, and an alpha carbon. But if we take a minute and think about acids and bases, we can see that we have a carboxylic acid group, which is acidic, just like the name implies, and those typically have pKa values of about 2, right? And if you have an amino group, those tend to be basic and have a pKa of about 9. So now, if we think about reactions taking place under physiological conditions or at about pH 7.4, what would be the ionization of those two groups? In other words, would the carboxylic acid group be protonated or deprotonated, and would the amino group be protonated or deprotonated? Yeah, when the pH is above the pKa value, the Ka value or the pKa value is really referring to the acid losing its proton, right? It's the acid dissociation constant. So when the pH is well above its pKa, that particular group, ionizable group, would be deprotonated. So in this case, the carboxylic acid group would be a carboxylate. So now if we think about the amino group, its pKa value is well above the pH under physiological conditions. So that means that this group would actually be protonated. So it's actually CH3 with a proton, right? Something to keep in mind. So at the pH above the pKa, the ionizable group, okay, the ionizable group is deprotonated. Right? So when the pH is above the pKa of that specific group, it is deprotonated. And when the pH is still well below its pKa value, it's still protonated in solution. All right. So that's an important concept when it comes to amino acids. So if you take a look at that particular amino acid, that would be the amino acid of the simplest of all of them, which is glycine, right? And at that particular pH, or at that particular ionization state, the molecule exists with no net charge, and we call those Zwitter ion, right? It's when the molecule has a net charge of 0, right? The molecule has a net charge of 0, right? So we refer to it as a Zwitter ion. So what we can do is actually calculate the pH at which the molecule would have a net charge of 0. That becomes very useful when we start using chromatography to separate a mixture of proteins, or when we're using gel electrophoresis. Being able to identify the charge of a particular amino acid or a longer polypeptide chain is useful. So how exactly can we determine when the molecule has a net charge of 0, right? That brings us to a different concept, and that's really basically the isoelectric point. Right? What's the isoelectric point? It's really referring to when the molecule exists as a Zwitter ion, but it's really the pH at which the molecule has a net charge of 0. The pH at which the molecule has a net charge of 0, or in other words, exists as a Zwitter ion. Has a net charge of 0, meaning it's a Zwitter ion. All right. So how can we determine the isoelectric point? Well, the isoelectric point has the abbreviation lowercase p, uppercase I, right? Well, if the charge of the molecule depends on the pH of the solution and on the pKa of those ionizable groups. So when we determine the isoelectric point, it's always between two given pKa values, all right, when the molecule has a net charge of 0. So we use the formula for the isoelectric point, that the isoelectric point is equivalent to two pKa values, right? I'm going to call it pKax and pKay, right? Divided by 2. So if we were to calculate it, the isoelectric point for that particular glycine, it's really a bit above 2 and a little above 9, but I'm just using 2 and 9, as an example. It only has 2 pKa values, so it would be 2 plus 9 over 2, or really you have 9, 10, 11. 11 over 2 is about 5.5 in this case, right? So when the pH is 5.5, if we only have glycine in solution, glycine would have a net charge of 0. If you're at a pH 7.4, glycine would still have a net charge of 0, right? Up until you reach a pH of about the pKa of glycine, right? So can we write an equilibrium that explains this a bit better? We can. So I'm going to draw everything protonated. So suppose the pH is very low, below pH of 2, then all the groups would be protonated, right? When the pH is above the pKa, they deprotonate, but if something is at a pH of 1, everything within that particular molecule will be protonated, meaning all basic groups will have a positive charge, and the acidic group would be neutral. Well, once the pH increases and passes pKa2, the carboxylic acid group would be the one that would deprotonate. O minus, NH3 plus, right? And then we have the next equilibrium, right? So those two equilibria between when the first proton dissociates and when the second proton dissociates are really the pKa values, right? This is pKa, I'll just call it 1 because it's the first one or the lowest one, and then pKa2. So 2 and 1. And those would be 2 and 1 right here. Or it's not always the first and the second pKa value, but in this example, there's only 2 pKa values. So when did the molecule exist as a Zwitter ion or have a net charge of 0? If you notice, it existed as a Zwitter ion right between the first pKa value and the second pKa value, right? So those are the 2 pKa values that we use when we calculate the isoelectric point. So we'll do another example of isoelectric points in a little bit, but for now that's a brief idea of what an isoelectric point is, how do we calculate it, and why do we draw an amino acid with the carboxylic acid group being deprotonated while the amino group being protonated. All right, so let's erase this and draw the amino acids. All right, this is taking some time to clean up, but we will get this done. Is it clean? Not yet. All right, you know, it's not easy writing backwards on these boards, so. Okay, as clean will be. All right, so I'm going to show you a way of remembering the 20 different amino acids, remembering the structure, and instead of having to sit down and correlate and group amino acids as acidic and basic, charged and not charged, and putting yourself where you're trying to remember lists, you know, and grouping them. As long as you know the structure, right, as a chemist, you should be able to identify the properties, to predict if the amino acid will form ion pair interactions or not, right, based on the charge, or whether the amino acid will be soluble in an aqueous environment or not, again, based on the structure of the amino acids. So we're going to start with the simplest of the amino acids, which is glycine, right? So we have the carboxylic acid group, and we have the amino group, right? It's the simplest of all. All it has is 2 hydrogens at its alpha carbon. That's the alpha carbon, and we typically use the Greek nomenclature when we are referring to amino acids. So that's glycine, gly, or G, right? Similar to glycine is alanine. Alanine has 1 methyl group. Alanine, ALA, or its 1-letter abbreviation is A. And yes, you do need to know the full name, 3-letter abbreviation, and 1-letter abbreviation. All right. And then similar to it is so it's like you have the alanine, but you also have 2 more methyls which look like a V, and here comes valine. Valine, VAL, or V. Okay? And then, similar to valine is leucine. So, in valine, you have alpha carbon, and then at the beta carbon, you basically have the 2 methyl groups. Well, in isoleucine, you have an alpha carbon, beta carbon, gamma carbon, and then you have the 2 methyl groups, right? So you have the alpha, beta, and then gamma. And that would be leucine. LEU, or L for leucine. Well, similar to leucine is isoleucine. That's a positive charge. And in isoleucine, that methyl group, instead of coming off of the gamma proton, it actually comes off of the beta carbon. So alpha, beta, gamma, delta. Alpha, beta, gamma, delta, right? Alpha, beta, gamma, delta, and that extra methyl in isoleucine comes from the 2nd carbon instead. All right, so here is isoleucine. And its 3-letter abbreviation is similar to that of leucine, but put the I and then LE, right? And isoleucine. All right. If we were to group amino acids based on properties, where would we put such amino acids, right? They all have aliphatic, or just hydrocarbons, in their side chains, so they're non-polar, they're not charged, right? So you would think that such amino acids in a folded protein would be towards the inside of a folded protein, away from the aqueous environment, for the most part. All right. And whatever group we have attached to the alpha carbon, we call that the side chain, right? That's what gives the amino acid its property, the side chain. So now we're going to draw 2 more, right? One that is similar actually to alanine, right? So alanine has a methyl, and here is a methyl. But serine is an amino acid similar to alanine, except that it has a hydroxide group. And that's serine, or S, right? Very similar to alanine. And then we have one similar to valine that also has a hydroxide group. So draw valine, but take away one of its methyls and replace that by the hydroxide, right? That would be threonine, or THR, or T. All right, so far here goes 1, 2, 3, 4, 5, 6, 7. 7 out of these 20 amino acids. Not too bad, right? Okay, so now we're going to draw some of the aromatic amino acids. All right, so all of those were basically nonpolar. Serine and threonine are polar because they have the hydroxide group attached to it. That's not ionizable. It does not have a pKa value. Right? So now we're going to draw some of the aromatic amino acids. And I think I have space. All right. So which amino acids are aromatic? Right? One that we can draw is, we can draw all of them, is a methyl, and then that methyl group is basically attached to a benzene ring, right? And we call that phenylalanine, PHE. But if you think about phenyl, F, so its one letter abbreviation is actually an F. And what it has is a phenyl group, and here is a phenyl group, and then an alanine, and alanine is one methyl, right? So that's phenylalanine. Similar to phenylalanine is tyrosine. And I missed the charge. Again, we have the methyl, we have the benzene ring, but we also have a hydroxide attached to it. And we call that tyrosine, or TYR. And if you think, so we already used the T for threonine, tyrosine, there's the Y, and the Y is its one letter abbreviation, right? So that's tyrosine. What are some of the other aromatic amino acids that we could draw, right? There's one. That has 2 rings. So again, we're going to draw one methyl, and we have the double bond right here, and then we have the benzene ring, and that is known as tryptophan, right? TRP. It's the one that has one of the one-letter abbreviations that might be hard to remember. It's a W, but it should remind you of the 2 rings, the W, tryptophan, right? So that's tryptophan. Okay, there's one amino acid that is slightly different than all of the other amino acids, right? Glycine is different than all of the other amino acids because its alpha carbon is not chiral, right? Has 2 hydrogens attached to it. All of the other amino acids that we draw, the alpha carbon is chiral. Well, proline is different in a different way. So if we draw, or when we do draw proline, right? So here's the carboxylic acid group. Its nitrogen, or its amino group that's directly attached to the alpha carbon, is part of the ring of proline. So that's proline. And now this nitrogen has 2 bonds, so it really, if we draw it on its own, it only has 2 hydrogens and a positive charge. Proline. Pro or P. All right. So we'll see proline specifically at turns in a folded proteins, right? You could think about the structural hindrance that a proline would cause, which causes the molecule to basically, or a peptide sequence to fold, right? So there goes proline. There's one more that has a charged side chain, an aromatic side chain, which is which will be your friend in biochemistry. So here's an alpha carbon and a nitrogen right here, 2 carbons, a double bond, a nitrogen, and a nitrogen. So this one has a hydrogen, and there goes a double bond right here, right? And we call that particular group an imidazole group. Right? The imidazole group of histidine has a pKa around 6, right? Which means it can act as an acid or a base. So it's involved in acid-base reactions. It is also a ligand for the binding of different metal ions as well, and we'll see it at the active site of some proteins. All right. Any of the other amino acids right here have an ionizable side chain? No, it's really only imidazole. So at pH 6, this nitrogen would be deprotonated, but if it was at a pH 4, this nitrogen would be protonated. All right. Okay, so now we're going to draw some other amino acids. So that's quite a number of them already. Right? Hopefully that was kind of easy to remember. So I'm going to have to erase. All right, so what else are we missing? Which amino acids are we still missing? Well, there are some amino acids that are charged and basic. We can put histidine with that group of amino acids as well. All right, some amino acids are basic, meaning they have a basic charged side chain, right? Or a basic group in its side chain. So O-. And one such amino acid is lysine. So we do use the Greek nomenclature. So alpha, beta, gamma, delta, epsilon. And then we have an amino group. Right? And that is lysine. L-Y-S or K. Yeah, it's a bit more challenging to remember the K. So alpha, beta, gamma, delta, epsilon. So we call this amino group the epsilon amino group. And it has a pKa value of about 10.5, right? For the R group. So again, for the carboxylic acid group and the amino group, just know one is about 2 and one is about 9. And then there's only few more that have a side chain ionizable group that you need to remember or be able to estimate the pKa of, right? So know that lysine is about a pKa of 10. All right. Well, another one is arginine. So arginine has the same number of carbons of lysine, but it's drawn a little differently. So alpha, beta, gamma, delta. And then instead of having an epsilon carbon, we actually have a nitrogen, all right, an NH. And then we have our epsilon carbon, which is also attached to two nitrogens, NH2, NH2 plus, right? It's of the most basic side chains and has a pKa of about 12.5, right? So that is known as arginine, or ARG, or R, right? Arginine, so R. All right, so those are basic. Histidine could be grouped with a basic, right? And something to keep in mind that when we write the pKa value of those amino acid and its side chain in a folded protein where you have a sequence of about 10 or more amino acids in sequence, and when the protein is actually folded in a specific way, those pKa values vary from when the amino acid exists on its own, right? Because those ionizable groups are actually affected by what we call the microenvironment of that folded protein. So it's not always 12.5 in every single arginine in every single protein. It varies. And that's why it's okay to know, to be able to estimate what it is. All right. And then we have two that are acidic, right? Having a carboxylic acid group in their side chain, O minus. All right, so we have an alpha carbon, beta carbon, and then draw a carboxylic acid group, right? And we call that aspartic acid, or asp, or D. Okay, so that's aspartic acid. When it is deprotonated, when its carboxylic acid group in its side chain is deprotonated, we also refer to it as aspartate, right? 8 versus IC acid. If it's deprotonated, so aspartate is the same thing as aspartic acid. Well, similar to aspartic acid is glutamic acid. O minus. So alpha, beta, gamma. So we have alpha, beta in a carboxylic acid group, but in glutamic acid we have an extra carbon, alpha, beta, gamma, and then a carboxylic acid group, right? And we call that glutamic acid. Its three-letter abbreviation is GLU, G-L-U. But if you think about the word glue, glue ends with an E, and the one-letter abbreviation of glutamic acid is E, glue. All right. And just like aspartic acid, when it's deprotonated, it is known as glutamate. All right. Now, obviously, based on the structure, both aspartic acid and glutamic acid would have a pKa value for its side chain. Now, they're very similar in structure, and the only difference is really in carbon. So, which one would you expect to have the higher pKa value? Which one is less acidic, aspartic acid or glutamic acid? Yeah, glutamic acid is less acidic. You have more carbon, right? Inductive effect, longer carbon chain, less acidic. And in fact, glutamic acid has a pKa of about 4.3, roughly, whereas aspartic acid has a pKa of about 3.6, I want to say, something like that. So they vary slightly. So do you really have to remember exactly what they are? No, but if you ever encounter a sequence and you're given pKa values and that sequence has both aspartic acid and glutamic acid, just remember that glutamic acid has an extra carbon, which makes it slightly less acidic, and its pKa value is slightly higher. All right, so there are two amino acids that are very similar to aspartic acid and glutamic acid. But before If you ever forget which one has the extra carbon, D comes before E, right? A, B, C, D, and then E. E has one extra carbon than D, right? That's another way to remember that aspartic acid has one less carbon. All right. Well, there are two that are very similar to glutamic acid and aspartic acid. One is known as asparagine, or ASN, right? It ends with an N, and its one-letter abbreviation is N. All right. How is asparagine similar to aspartic acid? Well, we still have alpha, beta, alpha, beta, alpha, beta, and then we draw the carboxylic acid group, but instead of it being a carboxylic acid group, it actually has an amino group, right? Otherwise, it's the same. Glutamic acid also alpha, beta, gamma, and then we have a carboxylic acid group, but replace that hydroxide by an amino group, right? And instead of glutamic acid, this would be glutamine and glyn. Instead of the U, we have the N, and the N is really the nitrogen, right? And its one-letter abbreviation is actually Q. Think about it as cutamine, right? Q. Right. So those are really the 20 amino acids. So if you think about it, one amino acid should always remind you about how to draw the next amino acid and so forth. Meaning, if you know how to draw aspartic acid, glutamic acid is only one extra carbon. Now, if you know how to draw aspartic acid, you know how to draw asparagine, right? Replace that hydroxide by an amino group. Likewise, if you know how to draw glutamic acid, you know how to draw glutamine. Lysine and arginine, I feel that knowing the Greek nomenclature helps you. So when you're drawing it, you're just saying alpha, beta, gamma, delta, epsilon. This is known as the epsilon amino group. Both arginine and lysine have the same number of carbon atoms, but they're different. And if you think this has more nitrogen atoms, right, which makes its pKa much higher than that of lysine as well. And we call this group really a guanidinium ion group, right, or a guanidinium group. Okay. Well, I hope that this video was helpful in terms of determining the isoelectric point and in terms of being able to identify the structure of different amino acids and be able to learn all 20. All right, but I'm going to do an example of an isoelectric point once again in a titration curve, and we'll do it for arginine, all right? So let's do that before I let you go. So we're going to do it for arginine. Okay, so its imidazole, its guanidinium ion group has a pKa of about 12.5. Its carboxylic acid group will have a pKa of about 2. Just going to estimate. Its amino group has a pKa of about 9. All right, right around 9. So how do we determine its isoelectric point? Well, let's take a moment and think when the protein is completely, everything is protonated, meaning all the basic groups are protonated and all the acidic groups are protonated as well, meaning that this carboxylic acid group will actually be protonated, right? So that's at a very low pH, below pKa 2. Everything within the molecule will be protonated. So if you think about a molecule or an amino acid that has 2 basic groups and 1 acidic group, its overall charge at that point of time will be 2, right? And every time it loses a proton, its charge will decrease. So it'll go from +2 to +1 to 0 to -1. How do I know it's stopping at -1, not at -2 or -3? That's because it only has 1 acidic group. So the acidic groups will end up being negatively charged when everything deprotonates. The basic groups end up being neutral when they're deprotonated, right? So now let's draw the equilibrium, right? So we have arginine, and arginine is losing a proton, right? It's going to lose its most acidic proton first. So this is its most acidic proton, so it's going to lose its most acidic proton first. Everything else will really remain the same. So alpha, beta, gamma, delta, and then really the epsilon is the NH, and then NH2, right? So it lost its very first proton right here. So that happened above pKa 1. So if you have a molecule and it has 3 pKa value, really when we number them, 1, 3, 2, we go by order from the lowest pKa value to the highest pKa value, right? So this particular ionization occurred after pKa 1, right? And when the pH of the solution starts to increase above pKa 2, what happens is the second most acidic proton, and that would be at pH 9, would deprotonate. So NH2, right? It deprotonated to alpha, beta, gamma, delta, alpha, beta, gamma, delta, and then we have the NH, all right, so the second most acidic proton deprotonated past pKa 2. So now what happens once you pass the third pKa value, right? At a pH past the third pKa value, then the next most acidic proton would deprotonate. One, two, three, 4, or alpha, beta, gamma, delta, and this is right at epsilon. All right, so it deprotonated. Okay, so that's what we have, right? So let's do things. 1, draw a titration curve for arginine. 2, calculate the isoelectric point for arginine. How exactly can we calculate the isoelectric point? So if you take a look at the different equilibria showing the ionization of the groups within histidine, between which 2 pKa values does arginine, not histidine, does the arginine exist as a Zwitter ion, meaning having a net charge of 0, right? You have +2, so it's +2. You have +2 minus 1, that's +1. You have +1 minus 1, so 0. So right here, it exists as a Zwitter ion, right? Meaning it has a net charge of 0. And that really took place between pKa 2 and pKa 3. So if we were to calculate the isoelectric point for arginine, it would be pKa 2 plus pKa 3 divided by 2, right? It would be those 2 particular pKa values, because right in between both, arginine had a net charge of 0. So that's its isoelectric point. All right, so now can we draw a titration curve? Sure we can. All right, so, and what are we plotting? Well, we're plotting pH versus the protons that are dissociating, right? So really, each time a proton was lost in that particular equilibrium, right? So the proton that dissociated, right? Or really, equivalence of protons dissociated. How many protons do we have? 1, 2, 3, right? So 1, and we'll draw one at 2, and then we'll draw one at 3. Right, it's not so even. All right. And the pH. So 2, 4, 6, 8, and 10, and 12. All right, didn't realize I'm above. Okay, so what else can we say? Do you recall the Henderson-Hasselbalch equation? Let's see. When the pH is equal to the pKa plus the log of the conjugate base over the acid, right? And what we had said is that when the concentration of the acid and the conjugate base is exactly the same, the pH is equivalent to the pKa value. When would that happen? At the first equivalence point, at the second equivalence point, at the third, or right in between? Right in between, right? If you're adding a base, once you have half an equivalence of base, half of the acid that you have in solution, or half of those acidic protons, will deprotonate, right? And the remaining half will exist still as being protonated. So that really occurs at half the equivalence point, all right? So at 0.5, at 1.5, and at 2.5, what happens is that what exists between the acid and the conjugate base, is equal concentrations of both, right? When you only added half an equivalence of base, or when the acid only lost half of its protons, that means that half of its acidic proton, right? Or half of the acids in solution are now deprotonated. All right, it didn't lose half of its protons. You have so many molecules, right? So many amino acids in solution, and half of those deprotonated and became the conjugate base, right? Okay, so that occurs when the pKa is equivalent to the pH of the solution. So we can label that on a titration curve. So it's about 2. In the second equivalence point, it's really right about 9. And at the third equivalence point, it is right about 12.5. All right, and within that region of a titration curve, the addition of very small amount of base will cause little change. Right at the 1 equivalence point, at the second equivalence point, and at the third, what happens is the majority of what you have is the conjugate base, right? At the second equivalence point, the majority of what you have is the conjugate base of the solution. Past the third equivalent point, the majority of what you have is basically, or what you have in solution is the conjugate base. All right. If you're below the first half equivalence, then what you have most in solution is still the acid. All right. And the buffering capacity typically for a given buffer is plus or minus 1 of its pKa value. Meaning if you wanted to prepare a solution, a buffered solution at a pH of 7, you would have to pick an acid and its conjugate base, where the pKa of that particular acid is within plus or minus 1 of pH 7. So anywhere between 5 and, or anywhere between, yes, no, 6 and 8, right? Plus or minus 1. So has a plus or minus 1 region here that we can label as well. So that's anywhere really between 10 and 9. All right, that is the region when very small changes, or where the change of the pH of the solution is very small, as the amount of the as you know, a number of equivalents of bases being added. Okay, so meaning very small amount of the pH changes very little as the amount of base is being added right within half the equivalence point and plus or minus 1 of that region. So now if you wanted to draw the titration curve, we need to keep in mind that at the first equivalence and at the second equivalence, what will happen is there will be a dramatic change in pH, because now what you have in solution is the conjugate base, right? And right within the plus or minus 1 region of its pH, when the pH is equal to the pKa value, that plot will level off somewhat, and that's really the buffering region for a given buffer. So it's going to start, does it start right at 0 or above 0? It's all relative to what we're starting off with, so start anywhere with it, right? It kind of levels off right here, and right at 1 it's going to dramatically increase, it's going to level off, dramatically increase, and it will go up, right? Now, some titration curves, if you flip through the textbook, you won't really notice this dramatic increase right at 1, right at 2, and it's all relative to how close those pKa values are to one another. But that's an easy way for you to sketch a titration curve. So hopefully you understand how to stretch a titration curve. You are able to determine the isoelectric point of a given peptide, and you can still correlate and understand that Henderson-Hasselbalch equation. All right, so we call that particular point half the equivalence point. All right, and we have half the equivalence point right here, and then again we have half the equivalence point right here, right? But this is really the equivalence point. And this is also the equivalence point. That's the first equivalence point, and that would be the second equivalence point, right? One of those equivalence points is equal to the isoelectric point, or is equivalent to the isoelectric point. And that would be the second equivalent point in that particular graph is equivalent to the isoelectric point of arginine when it exists as a Zwitter ion. So if you were asked to label the isoelectric point of a specific amino acid or a sequence, a peptide sequence, it is equal to one of its equivalence point, either the second, the first, and so forth. All right, well, I truly hope this was helpful. If not, let me know, and I'll fix it next time.